which is option B, 80%. Right. So I want to go over the question again. I'd like to go over the question again. Okay, the question says, all right, let me get the question. All right. The question says a wheel and axle is used to raise a load whose weight is 800 Newton. So this is the weight or weight, and a force of or effort of 250 Newton is applied. As I represented my effort with here, 250 Newton. If the radii of the wheel, which is capital I, that's the radius of my wheel, is 800 millimeter, and the radius of the axle is 200 millimeter respectively, find the efficiency of the machine. And remember, I said efficiency is equal to mechanical advantage over velocity ratio. So what I want to do is I want to calculate the velocity ratio separately and the mechanical advantage separately. So now, for me to get my mechanical advantage, in one of our classes, I've explained all of this. I said mechanical advantage is equal to load over effort. So I've explained it in one of our classes. So if you miss this, you can just go back to the class. So my load over effort. My load is 800 Newton, and my force is 200, and my efforts rather. My effort is 250 Newton. So if I divide it, I have 3.2. 3.2 is my mechanical advantage. Now moving down to my velocity. Wheel of the radius of the wheel divided by the radius of the axle, so which is capital R divided by small r. So what is the radius of my wheel? The radius of my wheel is 800 millimeter. Why the radius of my axle is 200 millimeter? So I simply divided 800 by 200. So dividing 800 by 200, I have 4. So my velocity ratio is 4 and my mechanical advantage is 3.2. So what I'm going to do is I'm just going to impute this. So the efficiency is mechanical advantage over velocity ratio times 100 over 1. My mechanical advantage is 3.2. Why my velocity ratio is 4? So after dividing this 3.2 by 4, I add 0.8 and times 100 give me 80%. That's why I have my answer as 80%, which is option B. So the correct answer here is option B to that question. All right. So now I said types of machine. I gave you the types of machine. I said lever, pulley system, wheel and axle, inclined plane. Okay, all right. So we'll be moving now to from wheel and axle. We've done lever, we've done lever, we've done pulley system. Now we just finished doing wheel and axle, so we'll be moving to inclined plane. So now for inclined plane, I'll be explaining this way. Inclined plane, velocity ratio in an inclined plane is calculated with the formula L over H. All right, I'm going to explain. Inclined plane, this is L over H. The L is distance moved by effort, and then distance moved by load. Inclined plane is simply a type of machine in which we have a horizontal plane surface inclined at an angle to the horizontal, or we have a plane surface inclined at an angle, a particular angle to the horizontal. That's simply an inclined plane. Used to lift load. For example, you lifting a cement or a drum to the top of a truck through a plan. That's an example of inclined plane. So I have something like this. I have this. Okay, so let me say this is the ground floor, and then this is the base of a truck. And I'm trying to move a drum from this point to this place. So now the distance moved by the load is going to be from here to here because it just moved from this point to this point. Why the distance moved by effort is going to be from here to here. Are we all right? So this place is going to be L. Why this place is going to be H? So which means my L here is the distance moved by effort. The effort I used to move this particular drum. Let me see, this is my drum. Moving this drum from this point here, from this point from the ground level to the base of this truck is the distance moved by effort. Why this height here is the distance moved by load. That is, the load is moving from the bottom or from the floor to the base of the truck. I think they are good. So now the velocity ratio of a an inclined plane machine is calculated by distance for distance moved by load, which is L over H. All right. You say the velocity ratio is equals to 1 over sine theta. So now let me say this guy here is theta. The angle here, this um this plane surface is inclined at an angle of theta to the horizontal. It means my velocity ratio can be calculated as 1 over sine theta. Or you can say my velocity ratio is distance moved by effort over distance moved by load. I think we're good. Okay, so now I'll take an example. So this theta here is my angle of inclination, as the angle at which the plane surface is inclined to the horizontal. Okay, all right. We'll take an example now. It says an inclined plane which makes an angle of 30 degrees with the horizontal, has a velocity ratio of, okay, it says an inclined plane which has an angle of 30 degrees to the horizontal, which means my theta is 30 degrees, has a velocity ratio of, okay, so it's asking me to find the velocity ratio of this particular machine. So I'll just say, I just said velocity ratio of an inclined plane is 1 over sine theta, right? So I'll say 1 over sine theta. So what's my theta? My theta is angle of inclination, which is 30 degrees, 1 over sine 30. What's sine 30? Sine 30 is 0.5. And then 1 divided by 0.5 is 2, right? So if I divide 1 by 0.5, I'll have 2, which means the velocity ratio of this particular inclined plane is 2. So which is option A? I think we're good. All right. I hope you guys are following me. So I'll just move to another topic right now, elasticity. All right. So we're moving to elasticity. So elasticity is simply the ability of the material to return back to its original shape or structure after it has been compressed or expanded by an external force or by an applied force or by particular load. So it is the ability of a material to return to its original shape and dimension after the removal of an applied force. The removal of an applied force could be in the shape of compression and could be in the process of stretching. It can be stretching or compression. All right. So now, under elasticity, we are going to be doing Hooke's law. We're going to be doing Hooke's law and then elastic limits, yield points, and then maximum load and all of that. Okay, so we'll be taking it one after the other. So how does Hooke's law relate with elasticity? Hooke's law simply states that the extension E of a material is directly proportional to its applied force, provided the elastic limit is not exceeded. Hooke's law states that the extension E of a material is directly proportional to its applied force, provided the elastic limit is not exceeded. So now Hooke's law is mathematically represented as, okay, I'm going to show you this now. So if the applied force is F, that's capital F. So if my applied force is capital F, what Hooke's law is just telling me is this applied force is directly proportional to my extension E of that material. So I have F is directly proportional to E. So I can say F is equals to K, where my K is my proportionality constant. Now this K is called force elasticity constant and it is measured in Newton per meter. This K is called force elasticity constant. This is my applied force. Why this is the extension E of the material? So the relationship between extension of the material and the applied force is simply F is equals to K. You don't forget this K is the force elasticity constant. So I have this as my Hooke's law. So Hooke's law is represented with formula F is equals to K. All right. So before we move to working examples, let me just quickly take you through elastic limit, yield point, and maximum load, and then fracture point. All right. So the elastic limit of a material is the point where the material no longer returns to its original shape or dimension after the removal of the load or applied force. Okay, so that's the elastic limit of a material. Okay, all right, let me show you something. Let me show you guys something. Hello? 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 All right, so here is the representation of Hooke's of the elasticity of the material, the elastic limit, the yield point, the maximum load, and then the fracture point. So I'm going to be explaining this one by one. So I said elastic limit of a material is the point where the material has exceeded, is the point where it can exceed, where it can still return back to its original point. All right. So now the yield point Here is the U point, here is the elastic limit, here is the maximum load, while here is the fracture point. All right. So I'm going to take this one after the other. I said my elastic limit of the material is the point where the material no longer returns to its original shape or structure. So now after this point, as you can see, it is directly proportional. So which means this is on a straight line. The graph is a straight line. So after getting to this point, it changes trajectory. So which means from this point, the elastic limit of the material after a force has already, if the force applied to the material has exceeded this amount of load, then it won't be able to return back to its original shape or structure or dimension. So now then the point of the material point where this material begins to deviate from Hooke's law, which means it begins to deviate from Hooke's law such that the extension is no more directly proportional to the applied force. So at this U point, the material begins to deviate from Hooke's law. So now moving to maximum load. Maximum load is simply the highest load or maximum load that the material can contain or it can support. So it's the amount of load or maximum force that this particular material can support. So this maximum load is represented with M here. So I'm just showing you the diagram. Here is the elastic limit. Here's my U point. Don't forget I said elastic limit is the point where which the material can no longer return back to its original point or dimension, its original shape, sorry, or dimension. Why this is the point where the the material begins to deviate from its law. This is the maximum load. That's maximum load is simply the maximum load the material can bear or it can support. Why the fracture point is simply the stage at which the material breaks into two or it fractures. So the meaning of fracture is simply it breaks into two. So now if you have a rubber or a spring or something and then you force it cuts into the fracture point. So there's a point whereby you can pull your string and then it comes back. So within that limit, it's still within the limit of Hooke's law. That's still following the principles of Hooke's law. So when it's elastic limit, it means it can no longer go back to its shape or structure. So which means if you compress it too much, it might not be able to go back to its original shape or dimension. Now, when it gets to this point, it begins to deviate from Hooke's law such that the force is no longer directly proportional to the extension of that material. Why at this point it can no longer bear that amount of, and when the load is too much for it, then it fractures. It breaks into two. So that's simply the explanation of all of this. So now I'll be moving to work done in an elastic spring. Work done in an elastic spring. All right. Okay, I'll just leave this there. The work done in an elastic spring can be calculated. Don't forget work work done. I'll say kinetic energy. And then work done is equals to kinetic energy. So I can simply say work done is equals to kinetic energy. So what I want to do is I want to find the kinetic energy of this. So what am I going to do? To find the work done in an electric spring, I'll just say work done is equals to half k squared. So now half k squared, E is the extension of the material, y k is my elasticity constant. So the work done in an elastic spring is simply half k squared. Your k is your force elasticity constant, while your E is the extension of the material. So now don't forget, over here I said the relationship between force and the extension of the material is F equals to K. So if I say F is equals to KE, I can replace this F with this. How? This is the same here as W is equals to half K times E, right? So now replacing this K here with F, I will say W, which is work done in an elastic spring, is equals to half. I'm replacing this K with F here, which is force, F times E. So which means the work done in an elastic spring can be calculated with this formula, which is half Fe, that's force times the extension, or average kinetic energy. Sorry, the elastic constant. The K is my force elasticity constant, then the square of the extension. So half Ke squared or half Fe, which is force times extension. So here are the two formulas you can use in calculating the work done in an elastic spring. So I'll be taking an example. So the example says calculate the work done on an elastic spring. All right, I'm trying to make this fast so we can cover as much as possible. And then I'll still break it down for you guys to follow. All right, it says calculate the work done on an elastic spring with a spring constant of 154 Newton meter, with initial length of 2 meter and a final length of 2.18 meter after being stressed by a force. So what I'm going to do is I'm going to write down my parameters here. So the spring constant, which is my K, spring constant, elasticity constant, force constant, same thing, it's my K, 154 4 Newton per meter. All right, the initial length, I can see that is L1 is 2 meter, while the final length is 2.18 meter. Don't forget, extension is simply the change in length, difference in the length of this material as far as it was stretched or compressed. So that's the extension. So now, after being stretched, the work done in an elastic. So they asked me to find the work done. I don't know the work done. So what I'm going to do here is, first of all, I want to find the extension. The extension is L2 minus L1, which is 2.18 minus 2. All right. So I'm going to subtract 2.18 from 2. So 2.18 from 2 is going to give me 0.18 meter. All right. So my extension here now becomes 0.18 meter. I think you guys are with me. So now what I want to do here is work done. I just said work done is equals to half K squared, isn't it? So now I know my E is 0.18 and my K is given as 154 Newton meter. So to calculate the work done, I'll just say equals to half times 154, which is my elastic constant or force constant, then times 0.18 times 0.18, or I can just say times 0.18 squared. So from here, I can say 2 can divide this, and now I have 77, correct? Yes, 77. And then I'll just say 77 times 0.18 times 0.18. So I'm just going to multiply 77 times 0.18 times 0.18, okay? All right, so I have my answer as 2.49. 2.49. Don't forget we are calculating work done. So work done is calculated in joules. So this is 2.49. So in my question here, the 2.5 joules. So which means my answer here is option A after approximating it to one decimal place. So now we'll move to the next example. All right, moving to the next example. It says determine the energy stored in an elastic material whose force constant is 1.2 times 10 raised to the power 5 Newton meter and extends by 2 centimeter. Okay, right? Force constant is 1.2 times 10 raised to the power 5 Newton per meter, rather. And then it extends by 2 centimeter. So the extension is 2 centimeter. Don't forget my extension, the standard unit of my extension should be in meters, not in centimeters. So what I'm going to do here is I'm going to convert this centimeter directly to meter first. All right, so how do I convert this centimeter to meter? I'm simply going to divide by 100, right? So I'm going to divide this 2 by 100, and I'll say 2 divided by 100 gives me 0.02 meters. So I've converted this to meter. So now what I want to do here is I say work done is equal to half K squared, right? So now my K is 1.2 times 10 to the power 5. Why my K is, why my E, which is the extension, is 0.2, 0.02 times 0.02. All right, so I'll just divide this directly. I'll say 2 divided by this will give me 0.6 times 10 to the power 5. 0.02. So what I'm going to do is I'm just going to multiply all of this. So multiplying all of this, that's going to give me so when I multiply all of this, it gave me 24 joules. So I multiplied 0.6 times 10 to the power 5 and 0.02 times 0.02. So it gave me 24 joules. Don't forget we are calculating the energy stored in the spring. So the energy stored in the spring should be calculated in joules because the unit of energy is joules. So that's why my unit here is joules. So my answer here is 24 joules. So I'm going to check the answer with the correct option. So that should be option A. So my correct answer here is option A. The answer to that question here is option A. So now, before we move to the next topic, let's take one more example and then we'll move to the next topic. Okay, so all right, the question says if a wire is 30 centimeter, okay, if a wire 30 centimeter long is extended to 30.5 centimeter by a force of 300 Newton, find the strain energy of the wire. So that is this still the same thing. I'm just showing you different. The first, don't forget, just look at the methods they're using to ask the question. The first one says the work done in the spring. The second one said the energy stored in the spring. Why the third one is telling you the spraying energy of the wire. So I'm just giving you, they can ask you in different methods, but then everything's still meaning the same thing. So when you see something like this, you know you are using this formula, W equals to half K squared. All right. So what I'm going to do here is I'm just going to write out my parameters first. The question says if a wire 30 centimeter long is extended to 30.5 centimeter by a force of 300 Newton. So the force of 300 Newton. So which means initially the length of the wire is, which is L1, is 30 centimeter. Why after being extended, it was the length became 30.5 centimeter. So now I'm going to find the work done or the energy stored in the string or the strain energy of the wire. So this is what I'm asked to find. So firstly, I don't know the extension of this, so I'm going to find the extension. That's the extension of the wire of the spring. Okay, so for me to find my extension, I'll say L2 minus L1. But don't forget this L2 and this L1, they're in centimeter. But then the standard unit for calculating extension or calculating length, the standard unit should be in meter. So I'm going to convert this to meter first. So converting this to meter, I'm simply going to divide 30 by 100. So if I divide 30 by 100, I shall have 0.3. So this will become 0.3 meter. All right. So I'll also divide this by 100 and I'll have 0.305. That's if I divide it by 100. So I have this as 0.3 meter and this as 0.305 meter. So for extension, I said extension is equal to change in length, right? L2 minus L1. So L2 minus L1 is simply 0.305 minus 0.3. So I'm simply going to subtract this on this. So this is going to give me 0.005. Okay, so the difference or the extension of that wire or the energy, okay, the question says the wire. Okay, so the extension of the wire is 0.05 meter. So this is my extension. So what I want to do is I want to find the energy strain of the wire. So I'll say here in this question, I was given my force, which is the force of the wire. So my work will become half F, right? Don't forget I gave you two formulas. I gave you this one, half F, half K squared, and then half F. All right, so with this half F, I'll say 1/2 times my F, which is my force, is 300 Newton, 300. Why my extension is 0.005. All right. So now from here, so this will become 150. That's if I'm dividing these two by 300, I'll just say 2 here 1, 2 here 150, right? 150 times 0.005. So what I'm going to do is I'm going to divide 150 by 0.005. Sorry, I'm going to multiply 150 by 0.005. All right, so that's going to give me 0.75. Don't forget we are finding the strain energy of the wire. So the unit is also going to be joules. So 0.75 joules. And my answer is option A. Correlates with my answer 0.75 joules. So that's it. Okay. Don't just example. I think by now you guys should be cleared. So these are just the steps you follow. You interpret the question, you follow the steps, and you have your answers, and you can pick it. But then just make sure that speed is very paramount when you're working in your UTME because you have 2 hours for all your questions. So which means for each topic you have just 30 minutes for each subject. Which means for each section I have to answer all these questions. You have to add speed everything you're doing. All right, so we'll move to another topic quick so we can just gather enough grounds. We say the topic will be temperature and thermal expansion. Temperature and thermal expansion. All right. So I said the new topic is temperature and thermal expansion. I hope my handwriting is not too tiny over there. So, all right. So what's temperature? Most of you say define temperature as the degree of hotness of the body or the place. Temperature is the degree of hotness or coolness of the body. But then I will define temperature for you as the sum total of the average kinetic energy of the body. So the average kinetic energy of the body is simply temperature. So temperature, some people define it as the degree of hotness or coolness of the body. But then you can also define it as the sum total of the average kinetic energy of the body. So temperature, everybody knows temperature is either measured in degree Fahrenheit or degree Celsius or Kelvin. So the 3 units of temperature is either degree Celsius or degree Fahrenheit or Kelvin. So those are the three unit of temperature. All right, so that's not where we are really going today. I just want to give you a brief explanation of temperature. So where I'm moving to really today is thermal expansion. So I'll be explaining thermal expansion now. So on thermal expansion, we have linear expansion, area expansion, volume or cubic expansion. So now we'll be doing um linear expansion. We'll start with linear expansion. So what's the definition of linear expansion? Linear expansion of a material is simply the change in length per unit length by degree rise in temperature. So it is denoted by alpha. So alpha, this will be, if you know this is alpha, it's a Greek letter, so this is alpha. So linear expansion is denoted with this alphabet, Greek alphabet, alpha. And then it is mathematically represented as, no, I said it is the change in length, that's L2 minus L1, which is extension for change in length, by unit length, per degree rise in temperature, which is theta 2 minus theta 1. I will explain all of this now. So, I mean, when I said this is linear expansion, I said it's a change in length. This is change in length. Per mu is divided. So, per unit length, this is the length. Then per degree rise in temperature. Rise in temperature is simply the difference in temperature. So now my degree rise in temperature can be theta 2 minus theta 1. So theta 2 is my final temperature, while theta 1 is my initial temperature. So how do I know this? So when the whole theory of thermal expansion is this: when objects are heated, they tend to increase in length. When metal objects or solid objects are heated, they tend to increase in length. So that's why you find that when you heat up objects, they kind of increase slightly in size. So that's just the issue of that's just the theory of thermal expansivity. But then what we want to work in with is the calculations here, which are going to be coming out in your UTME questions very well. So what I'm saying here is at my L1, this is the length of the particular object or particular body at a temperature of theta 1. Why at L2 will become the length of this body, of that same body at this particular temperature. So now, you remember I said when objects increase temperature, or when the temperature of objects increase, they tend to increase in size. So now, so let me say this is 20 degrees Celsius. The length of that material is L1 at 20 degrees Celsius. Now, at 40 degrees Celsius, the length of that material is increased probably by 0.01 meter or something. So now the temperature became, the length of that particular object became L2 at temperature of 40 degrees Celsius. So which means this theta 2 is my temperature at L2, while theta 1 means my temperature at L1. So you can call this final temperature, you can call this initial temperature, or you can call this final length and initial length. This is also initial length, L1 and L1. Why this is my linear expansivity? So the old theory of linear expansivity is simply the change in length, which is L2 minus L1, the amount of change that happened in length when this was changing, when the temperature was changing, per unit length and per degree rise in temperature, the rise in temperature. The rise in temperature, it was rising from 20 degrees Celsius to 40 degrees. When it's from 20 to 40 degrees, how do I find the rise in temperature? I'm simply going to subtract 20 from 40, which is going to give me 20, which means my degree rise in temperature is 20 degrees. So I can also write this as L2 minus L1 over L1 theta. So my theta is equal to theta 2 minus theta 1. So now this that I wrote here is simply the rise in temperature. Theta 2 is final temperature, theta 1 is initial temperature. Why theta is simply the rise in temperature? How do I calculate the rise in temperature? 40 minus 20 give me 20, right? Or let me say this is 10. Let me say this is 10. So 40 minus 10 is going to give me 30, right? So which means my degree rise in temperature is 30. Theta 2 minus theta 1. So you can write it as this: L2 minus L1 over L1 theta, or L2 minus L1 over L1 theta 2 minus theta 1. Anyone that is convenient with you, but the two mean the same thing. So this is linear expansion. Don't forget, it is represented by alpha. All right. So I already explained L2 is the final length, L1 is the initial length of the material, theta 2 is the final length of the material, theta 1 is the initial length of the material. Okay, sorry, initial temperature and final temperature, rather. Theta 2 is final temperature, while theta 1 is initial temperature. So this is the temperature at L2, while this is the temperature of the material at L1. All right, so let's take examples, working examples. Just take an example, and then I'll give you another take-home assignment. You can just practice with it. And then when you practice with it, you can come up with the solutions. If you get the solutions, then it means you're making progress. You understand what we are doing so far. All right. So the question says a brass measuring tape is correct at 20 degrees Celsius. A brass measuring tape is correct at 20 degrees Celsius. The value obtained when the length of a field is measured with the rule at 50 degrees Celsius appears to be 70.5 meters. What is the true length of the field? So simply, the first thing is you try to interpret the question. It says a brass measuring tape is correct at 20 degrees Celsius, which means it must have a particular length at that 20 degrees Celsius, which is L1. So L1 it is correct at 20 degrees Celsius, but it didn't tell me what is that length. I don't know it. So at 20 degrees Celsius is when it is correct. So that will become my theta 1, 20 degrees Celsius. Now, the value obtained when the length of a field is measured with the rule at 50 degrees Celsius. Now, there's a temperature rise from 20 degrees Celsius to 50 degrees Celsius. So my theta 2 now becomes 50 degrees Celsius. So now that length is what? 70.5. Don't forget I said L2 is the length at temperature 2, which is L2 is 70.5 meters. So the question says, what is the true length of the field? The true length of my field is L1. That's what I'm looking for. It now says take linear expansivity of Brazos 1.8 times 10 raised to the power of minus 8 per Kelvin. Sorry, minus 5 rather. Minus 5 per Kelvin. Okay, I forgot to tell you the unit of linear expansivity is per Kelvin. So don't have it at the back of your mind. The unit of linear expansivity is per Kelvin. So I'll just say this is equals to L2 minus L1 over L1 theta 2 minus theta 1. So what I'll do here is I'll just subtract theta 2 from theta 1. My theta 2 minus theta 1 is equals to theta, right? 50 minus 20. So this is going to give me 30, right? So I'll just say L2 minus L1 over L1 times 30 is equals to 1.8 times 10 to the power of minus 5, all right? My L2 is simply 70.5. So this will become 1.8 times 10 to the power of minus 5 is equals to 70.5 minus L1 over 30 L1. So what I'll do here is I'll of course multiply, bring this to this. Now I have 1.8 times 10 to the power of minus 5 times 30 L1 is equal to 70.5 minus L1. So if I multiply this, I'll simply have 5.4 times 10 to the power minus 4 is equal to 70.5 minus L1. So I'll just bring this, okay, there'll be an L1 here. So I'll bring this L1 to this side to become plus. So this will become 5.4 times 10 to the power minus 4 L1 plus L1 is equal to 70.5. What I'll do here is this will become 1.00054 L1. I'm converting this already to, this will become 70.5. So I'll just divide it, and when I divide it, I'll have my answer, and that will be the length of my material. So you guys can just take that as an assignment.